to study about the different types of representations of a state model. That is how we can represent a state model in different types. So let's start with our topic. So there are different ways in which the state model of a system can be represented. Broadly, they are classified into two types. First is the physical variable form and second is the phase variable form. The difference between these two types of representations is that in the physical variable form, the system is represented in the form of the physical variables of the system, and in the phase variable form, the system is represented in the form of its phase variables. So in the physical variable form, physical variables are used, and the state model, it is represented in the terms of the physical variables of the system. So here physical variables are used, whereas in the phase variable form, the phase variables are used to represent the state model. So let's study these two representations one by one. First, we will start with the physical variable form. So in the physical variable form, as the physical variables are used, so the representation of the system, it is quite easy, and through this physical variable form, it is directly related to the physical nature of the system. So let's study this physical variable form. So the advantages of the physical variable form, or we can say the features of the physical variable form, are here in this representation, physical quantities are chosen as the state variables, because for the state model representation, we will require the two equations, state space equations, and we have to choose some variables as the state variables. So here physical quantities are chosen as the state variables, which can be measured and controlled. It is directly related to the physical system because physical variables are used, so we can directly relate the physical system of the system through this representation. Then the solution of the state equations, they gives time variance of the state variables. So in time domain, the state variables will be represented. Now, any of these variables, they can be used for feedback, and hence the implementation is easy. It means that any of the physical variables, we can choose them for the feedback, and hence the implementation of the design of the system, it is straightforward or it becomes easy. So these are the advantages of the physical variable form. Now let us see that how the state variables they are chosen in the electrical and the mechanical system, and how we can represent the electrical and mechanical system using this physical variable form. So let us study that how the state variables are selected for the different systems. We will study for the electrical and the mechanical system. So let's start with the electrical system. So in the electrical system, we have resistance, capacitor, inductor. These are the three elements which are the components of an electrical network. So for an electrical network, the inductor and capacitor, they act as the energy storing devices. So for these energy storing elements, for inductor, we have the rate of change of current, and for the capacitor, we have the rate of change of voltage. So we can write that the rate of change of current, that is DIL by dt, and for the capacitor we have the rate of change of voltage. It means dVc by dt. So these two, they can be taken as the state variables in case of an electrical network. So whenever we want to represent a electrical network through this state model, so we will choose the rate of change of current as the state variable and the rate of change of voltage as the state variable for the capacitor. So this is for the electrical network. Now for a mechanical network. Now for a mechanical system, we have the basic elements as the mass, damper and the string. And the quantities we have just like in the electrical network, we have voltage and the current. And here we have the potential energy and the kinetic energy. So for a mechanical system, the potential energy and kinetic energy of a mass, they are functions of position and velocity of the mass respectively. Therefore, the position and velocity they are chosen as the state variables in case of a mechanical system. So for a mechanical system, we have position and velocity. So whenever we have an electrical network, we will choose the inductor current and the voltage across the capacitor as the state variables, and for a mechanical system we will choose position and velocity. Position is x and velocity is omega there, so we will choose their x and omega, or displacement and the velocity as the State variables. So let's start with the electrical system, how we can represent an electrical system in the physical variable form. So for an electrical network, we have to choose the inductor current and the capacitor voltage as the state variables. So our first step, this is the procedure. For writing the state space equations for an electrical network. The electrical network will have a resistance, an inductor and a capacitor. So in RLC network, how we can write the state space equations for an RLC network. Now first step will be to choose the state variables. State variables we have as the inductor current IL and the capacitor voltage. So in first step we will assign all inductor currents, and capacitor voltages as the state variables. Now second step, so in second step, select a set of loop currents and write the relationship between the state variables and their derivatives in terms of these loop currents. Okay. So in second step, you have to select a set of loop currents, apply KCL or KVL, then select some loop currents in that, and then write the relationship or write the equations relating the state variables and their derivatives. You have chosen the state variables as the inductor currents and capacitor voltage. So in terms of these inductor currents and capacitor voltage, you have to derive all the equations. Okay. Now third step, now in the third step, write the loop equations and eliminate all the variables other than the state variables from the equation. So you have to write in the second step, you have selected the loop currents and you have write the relationship between the state variables and their derivatives. Now in the third step, you have to write the loop equations and you have to eliminate all the variables other than the state variables. That is, you will get the equations in terms of the inductor currents and the capacitor voltages. So all the state variables will be removed and you will get the state model or the state space equations of the system in terms of the state variables. So this is how the state space equations or the state model of an electrical network can be derived. Now let's take an example so that you will understand that how we can write the state space equations for an electrical network. So let us consider an RLC network having a resistor, an inductor and a capacitor. The input voltage is VI. The voltage across the capacitor is VC. current across the inductor is IL, the current across the system is I, the current across this capacitor is IC. Okay. So this is an electrical network or an RLC network. Now we have to, in the first step, we have to take the inductor current and the capacitor voltage as the state variables. So we have the inductor current as IL and the capacitor voltage as VC. So what we will do, the current in the inductor at time t equals to 0. That means the time is t naught. So we can represent this inductor current IL as IL T naught. Okay. Now current, this voltage across the capacitor, it is VC. So voltage across capacitor at time t equals to 0, that is T naught, it will be VC T naught. So we have the voltage across the capacitor at time t equals to 0 will be VC T naught. Okay. So we can say that this, we have defined the state of the system at time t equals to 0, that is T naught. Okay. So the state of the RLC circuit at T naught, it is known as the initial state of the system. So state of the RLC circuit at time t equals to T naught, it is defined by the inductor current IL T naught and the capacitor voltage VC T naught. So these variables IL and inductor current and the VC T naught, IL T naught and VC T naught, they are known as the initial state of the system. Similarly, we have the inductor current at time t and the capacitor voltage at time t will be ILT and VCT. So these variables IL and VC, they are called the state variables of the system. So our first step was to choose the inductor current and the capacitor voltage as the state variables, and we have done that. Now second step is to write the loop currents. We will choose the loop currents and then we will write the equations representing or relating these state variables with the state variables and the loop currents. So we will write the equations for this circuit. We have the circuit as this RLC circuit. So we will use here the KVL, that is the Kirchhoff's voltage law. So the voltage across the resistor, then the voltage across the inductor plus the voltage across the capacitor will be equal to the input voltage. So using Kirchhoff's voltage law, that is KVL, we will write the equations. The first equation will be L DIL by dt plus R IL plus VC equals to VL. So this L DIL by dt is the voltage drop across the inductor, IL is the current across the inductor. Then we have RIL, because the current across these R, L and C, they are connected in series, so current will be same. Current across the inductor is IL, so this IL and IC, these three currents, they are same. So we can write here, instead of I, we can write IL also. So we have written here RIL plus VC is the voltage drop across the capacitor, and the sum of these three voltage drops will be equal to the input voltage. Then we have this IL equals to IC equals to I. Okay, because it is a series circuit, and in series the current is same, and this IC, it can be written as C dVc by dt. So current will be equals, the current across the capacitor will be equal to the voltage drop multiplied with the capacitance. So this is C dVc by dt. Now from here we can write that dVc by dt, it is equal to I upon C. From this equation we can write, and from this equation we can write the value of this DIL by dt will be DIL by dt, it is VI by L minus VC by L minus R by LIL. So we can write minus R by L. This is IL. We can write here I also, because I is equals to IL. Then we have VC. So we can write minus VC by L. Then we have VI. So it is plus VI by L. This is from first equation. We have kept DIL by dt here, and all the terms we have shifted to the right hand side. So it will become minus VC minus RIL, and this L will be in the denominator. So we have these two equations. Now output, it is equal to x1. The first is state variable. So y we have as x1. And we have here dVc by dt. So it is the differentiation of the capacitor voltage. So we can write here Vc dot, it is equal to 1 upon C I. So this is our first equation, because the third step is that we have to eliminate all the variables and we have to obtain all the equation in terms of the state variables. Here state variable is the inductor current, so IL or IC, or we can write I also. So our state variable is I. And our second state variable is the capacitor voltage, that is VC. So we have obtained one equation which is having only the state variable and its derivative. So this is our first equations. Now derivative of the state variable, it means that it is our state equation. Because in this equations all the variables they are present are the state variables. I is a state variable, VC is a state variable, so this is a state equation. Now we have to obtain the state model. So our state variables were the inductor current and the capacitor voltage. So we have to write the derivatives of these IL and VC dot. Then for IL dot, we have the equation here as DIL by dt. So it will be IL dot. IL dot will be equals to minus R by L I minus VC by L plus VI by L. Now VI, it is the input. VC and I, they are the state variables. So we will write here the state vector. Then we have to write here the matrix. So the coefficient of I is here minus R by L. So we will write here minus R by L. Coefficient of VC is minus 1 by L. So we will write here minus 1 by L, plus we have the input also. So input is VI and the coefficient of VI is 1 by L. So we will write here 1 by L. So the complete equation will become IL dot equals to minus R by L I minus 1 by L VC plus 1 by L VI, which we have obtained here. Now we have VC dot equals to 1 by CI. So here I and its coefficient will be 1 by C. All the other coefficients will be 0. So its equation will become VC dot equals to 1 by C I plus 0 VC plus 0 VI, because their coefficients are 0. The terms are missing in the equations. So we have xt equals to, we have IL and VC. These are the state variables. So xt, it is our state vector. So it will consist of the state variables IL and VC. Then we have A, the matrix, state matrix. So it will be this minus R by L minus 1 by L, 1 by C and 0. Because if we compare this equation with the state space equation or the state equation, then it is x dot t equals to axt plus b ut. Xt state vector, it is I and Vc. Then we have A, this minus R by L minus 1 by L, 1 by C and 0. Plus we have B as 1 by L and 0. And ut is our Vi. So we have obtained the state equation for the system. Then we have yt equals to x1. So we can write this as y is equals to, we have 1, 0, x1, x2, the two state variables, plus 0, and this is our input ut. So C is 1, 0 and D is 0 here. So we have obtained the state equation and the output equation of this electrical network. X dot t plus is equals to axt plus but, and yt is cxt plus dut. These are the state model or the state space equations of the system. So in this way, we can represent the electrical network in the physical variable form. We can obtain the state model of the system. Now, for a mechanical system. So for a mechanical system, we have position and velocity as the state variables. So let us see that what are the steps for writing the state space equations for a mechanical system. We will choose position and velocity as the state variables. So first step will be to obtain the mathematical model of the system by using the nodal method. Second step is to define the state variables Z1, Z2, Z3. In this way, define all the state variables. Step number 3 is third step is to arrange the state variables in proper state model equations. Step number 4 is Using these equations, write the state space equations. So these are the 4 steps by which we can write the state space equations or the state model for a mechanical system. First step is to obtain the mathematical model using the nodal method. Second step is to define the state variables Z1, Z2, Z3 till we will define all the state variables. Then in step number 3, we will arrange these state variables in proper state model equations, and using these equations we will write the state space equations of the system. Now let's take an example so that you will understand that how we can write the state space equations for a mechanical system. So this is a mechanical system, and for this mechanical system we will have to write the state space equation. So our first step is to draw the nodal diagram or obtain the mathematical model of the system using the nodal method. So first we will draw the nodal diagram. So using that nodal diagram we can write the nodal equations. So nodal diagram will be, we have two nodes x1 and x2 representing the displacements. Then between this x1 and x2 we have this spring connected. This spring is K. So we are having two nodes x1 and x2. Between them we have the spring K. Then we have this M1 and the damper D. In a mechanical system, the three basic elements are the damper, mass and the spring. So this mass, damper, they are connected to the displacement or to this node x1. So we have this mass M1 here, and then we have the damper. Now to this x2 we have M2 and this force Ft, external forces applied to it. So here we have M2 and this is our external force F. So this is the the mathematical model of the system, and we have drawn the nodal diagram for it. Nodal diagram. This is our damper D, x1 and x2 are the nodes. Now we will write the equations for these two nodes x1 and x2. At node x1, we have the equations. Due to this mass, we have the effect due to this damper and due to spring, because these three are connected to the node x1. So due to the mass, we will have m1 x1 double dot, that is d2x1 by dt square, plus due to the damper we have d, then dx1 by dt. So this can be written as x1 dot, plus due to the spring we have here x1 minus x2, because the effect is towards this node. So we have k x1 minus x2 equals to 0. So this is the nodal equation at node x1. Now at node x2, we have this force and this mass and spring connected to this node x2. Now this external force, it is opposite to these resisting forces, that is the spring and the mass. So we will have this external force Ft equals to m2 x2 double dot plus k. Here we will have x2 minus x1. because this time we have to consider for this node x2, so it will be x2 minus x1. So we have this. Now from this first equation, these are the two equations which we have obtained. So from this first equation we have m1 x1 double dot plus d x1 dot plus kx1 minus kx2 equals to 0, and second equation we have ft equals to m2 x2 double dot plus kx2 minus kx1. So we have these two equations. So this was our first step, that we have to obtain the mathematical model of the system using the nodal method. We have obtained the mathematical model. Now second step is to choose the or define the state variables as z1, z2, z3. So in this way we will define all the state variables. So second step is to select the state variables. So we will select the state variables as z1, z2, z3, z4. In this way we have to select. So we will take this first displacement x1 as our first state variable z1. Then derivative of this x1 dot will be z1 dot, and this will be our second state variable z2. Then we will have x1 double dot equals to, we have z1 double dot, or we can write z2 dot. So this is our state variables, because in the equation we have single differentiation of x1 also and double differentiation of x1 also. So for all these derivatives we have to define the state variables. Now our second displacement is x2. We will take this as our third state variable z3. Differentiation of this x2 or derivative of x2 dot will be z3 dot, and it will be our fourth state variable z4. Then we have 2 double dot, so we can write this as z4 dot. So in this way we have defined the state variables z1, z2, z3 and z4, and the derivatives of the state variables also we have defined. Now we have the two equations of the state mathematical model. We have the two equations as this. So here we have x1 double dot, x1 dot, x1, x2, x2 double dot, x2 and x1. So we will replace these derivatives of the x1 and x2 by our state variables. So in first equation we have m1 x1 double dot. So we will write m1 x1 double dot is what? z2 dot, plus we have dx1 dot. So dx1 dot is what? z2, plus we have kx1. So kx1 is z1. Then we have minus kx2. x2 is z3, equals to 0. So we have replaced all the derivatives by the state variables. Then we have the second equation, ft equals to m2 x2 double dot. x2 double dot is what? z4 dot. So we will write here z4 dot, plus kx2. x2 is z3, minus kx1, that is z1. So this is our second equation. So we have obtained these two equations. Now we will simplify them. We will obtain these equations in terms of the state variables and their derivatives. So from this equation, first equation, we can write z2 dot as minus of kz1 upon m1 plus kz3 upon m1 and minus d Z2 upon M1. We have obtained Z2 dot. We will shift all the variables to the right hand side and divide them by M1. Then we will get Z2 dot. Now from this equation, we have Z4 dot will be, we will shift all the variables to the left hand side and we will get Ft upon M2 minus K upon M2 Z3 plus K upon M2 Z1. So we have obtained Z2 dot, Z4 dot. Then we have to obtain Z1 dot also and Z3 dot also. We know that Z1 dot is what? Z2. So we will write here Z2. And Z3 dot is what? Z4. So we will write here Z4. So for all the four state variables Z1, Z4, Z3, Z1, Z2, Z3 and Z4, we have obtained their derivatives equation. So in these four equations, using these four equations, we will write the state space equations. We will have here Z1 dot, Z2 dot, Z3 dot and Z4 dot. We have all the four state variables. Then we will write the matrix. Z1 dot is what? Z2. Here we will have Z1, Z2, Z3 and Z4 plus we have our input as the external as the force which we have applied, the Ft4 on the system. What we have applied, the input is our Ft. So Z1 dot is Z2. Z1 coefficient will be 0. Z2 coefficient will be 1. Z3 coefficient will be 0 and Z4 coefficient will also be 0. Now for Ft it will be 0 because in the equation for Z1 dot we have only the Z2 and its coefficient is 1, so we have written here 1. Now Z2 dot, we have Z1 coefficient as minus K by M1, so Z1 coefficient will be minus K by M1. Z2 coefficient is minus D by M1, so we will write here minus D by M1. Z3 coefficient is K by M1, so we will write here K by M1. Z4 coefficient is not present here, so we will write 0. Ft coefficient is also not present, so we will write here 0. Now for Z3 dot, we have Z4 only. Z1, Z2, Z3 are missing, so their coefficients will be 0. Z1, Z2, Z3 is 1, Z4 is 0 and Ft is also 0. Now for Z4 dot, we have the coefficient of Z1 as K by M2. Coefficient of Z2 is missing, so it will be 0. Coefficient of Z3 is minus K by M2, so we will write here minus K by M2. Coefficient of Z4 is missing, so we will write here 0. Then coefficient of Ft is 1 by M2, so we will write here 1 by M2. So in this way we have obtained the state space equation for the system. This is our first equation, state equation. Now we will write the output equation. Output is Yt and Y, we have output as Y1 and Y2. So Y1 is our displacement x1 and Y2 is our displacement x2. X1 is what we have assumed in the state variables, that x1 is z1. X1 is z1 and x2 is z3. So x1 is z1 and x2 is z3. So if we write the equations for this y1 and y2, y1 and y2, we have the two state variables only. It is z1 and this is y2 is z. So this was our first equation and this was our second equation. First equation is our state equation because it is having all the state variables, and second equation is our output equation. So collectively these equation number 1 and 2, they are known as the state space equations of the system. And this is the state model of the mechanical system. So this is how we can write or we can derive the state model for a mechanical system using the physical variables. So this is what we have studied, the physical variable form representation of the state variable. First we have studied for the electrical network, and then we studied for the mechanical system. Now the second type of representation of the state model is the phase variable form. So now we will study the phase variable form. In phase variable form, the state variables or the are the phase variables. That is, the phase variables are chosen as the state variables of the system. Now, in the phase variable form, the systems which are represented by the transfer function or the differential equations, for those systems, it is easy to obtain the state model representation in the phase variable form. So this phase variable form, it is used in only those cases where the system is represented by a nth order differential equation or a transfer function. So there are two types of representations in the phase variable form. First is the representation of the system, which is given in by the differential equations, and second is where the system is represented by or given in the form of a transfer function. So first we will study the state space representation of an nth order differential equation. Now the nth order differential equation, it is given by So this is an nth order differential equation. Here the differentiation is having the power n. So the highest order derivative of the y is n. So this is our nth order differential equation. Y is the output, u is the input. Coefficients of the derivatives are a1, a2 till an minus 1, and the coefficient of the input is b. Now we will here choose the state variables. So first, let the first state variable is y. Y is our output. So y is taken as our first state variable. Then we will take the first derivative of y, that is dy by dt, as our second state variable. So we will take dy by dt, or it can be written as x1 dot, because derivative of y is x1 dot, and it will be taken as our second state variable x2. Similarly, the derivative of second state variable will become our third state variable. Derivative of third state variable will become our fourth state variable, and similarly our derivative of n minus 1 state variable will be our nth state variable, and derivative of our nth state variable xn dot will be our this differential equation, because xn dot will means yn dot. So this last equation, that is yn dot, this is xn dot. If we write from this nth order differential equation, this is yn dot. So all the coefficients, they will go to the right hand side, and this will become minus a1. This is yn minus 1 dot. This is a2 yn minus 2 dot. So it will become xn dot minus an. This is what? Minus an. Y is x1. Then we have minus an minus 1. This is x2. Similarly, we will have here a2. This is minus sign a2. Then we have xn minus 1. Then minus a1 xn. Then we have this plus but. So plus bu. So this is our nth state variable. We have defined all the state variables and their derivatives. Now if we write the equation, it in the equation form, then we have here x1 dot, x2 dot, then we will have last is our xn dot. This will be equal to, here we will have the coefficients, and here it is our state variables. State variables are x1, x2 till xn, plus we have our input, which is u. So x1 dot is x2. So we will write here 0, 1 till last we have 0. Then x2 dot is x3. So we will have 0, 0, then 1 till last coefficient is 0. Similarly, for the last equation xn dot, we have minus an x1. So x1 coefficient is minus an. Then minus an minus 1. Similarly, for xn, we have the coefficient as minus a1. Then plus bu. So we have all 0 till last we have b. So this is the state equation for this system using the phase variable form, and the system, it is represented in the nth order differential equation. Now in generalized way, if we write this is x dot, it is equal to ax plus bu. A is this matrix, B is this matrix, X is this state vector, and U is our input. So X is our state vector, n cross 1, because there are n components in it. U is our input vector, A is our matrix. This matrix is of the order n cross n, and B is again a matrix of n cross 1, because there are n components in this matrix. Now this form of matrix A, it is known as the Bush form, because it is having all the elements above this diagonal as 1 1 1, and all the other we have components as 0, and only the last row is present. So this type of matrix represented is known as the Bush form representation of the matrix. So this was our state equation. Now output equation. For output we have y equals to x1, x2 till xn. We have written here y is what? X1. We have taken y as our first state variable. So its coefficient will be 1 and all the rest of the elements will be 0. So y is equals to x1. This is our output equation. So y is equals to cxt plus dut. Here input is not present, so d is equals to 0. Only output is present and c is this matrix. So c is 1, 0 till last 0. And this matrix is known as the output matrix. So we have derived both the equations, both the state equation and the output equation. So in this way, whenever we have a system which is represented by a nth order differential equation, then we will take the output as our first state variable, and in this way we are going to define all the state variables. Then we will obtain the state equations and the output equation for the system. So this is first type of representation. Now in the second type of the phase variable form, whenever the system is given in the transfer function form, then how we can represent it or how we can obtain the state model for it. So now we will study the state space representation for a given transfer function. So let's take an example so that it will be clear to you that how we can obtain the state model of a system which is given in the differential equation form. So we have to obtain the state model of this system, and the differential equation for this system is given to us. Now here this y and having 4 dots means that it is a fourth order differentiation of the output y. This is third order differentiation, this is single order differentiation, and y is our output, u is our input. So this is we have obtained the we have the differential equation of the system. So first we will choose our state variables. Our first state variable will be our output y. So y is x1. Then y dot, or we can say x1 dot, will be our second state variable. Then y double dot, or we can say x1 double dot or x2 dot, will be our third state variable. Then we have y triple dot or x1 triple dot, x2 double dot will be x3 dot will be x4. That is our fourth state variable. Then we have y fourth order dot, that is fourth order differentiation of this y, that is 4, 1, 2, 3, 4, 4 dots we have written here, and we have the equation here for this fourth order. So y will be 8u minus 5 triple dot on y, then minus 7y dot minus 9y. So for this 8u minus 5, we have y triple dot, so y triple dot is what? X4. Then minus 7y dot, y dot is what? X2. Minus 9y, y is x1. So we have obtained this equation. Now y triple dot, it is what? X4 dot. We can write here x4 dot will be y 4 times dot on this. So we have all the equations. Now using these equations, we will obtain the state space equations of the system. So here we will have x1 dot, x2 dot, x3 dot and x4 dot, because we have 4 state variables, so their derivatives will be written like this. This will be a matrix. Here we will have all the 4 state variables. Because the derivatives of the state variable, it is a linear combination of the states plus the input. Input is what? Ut. Now x1 dot, see these equations here, x1 dot is x2, x1, x3, x4 are not present in it. So their coefficients will be 0. x2 coefficient is 1, x3 is 0, x4 coefficient is 0. So if we write the equation for x1 dot, it will be x1 dot equals to 0 x1 plus x2 plus 0 x3 plus x4 and 0 ut. Now for x2 dot is x3. So x3 coefficient will be 1. Rest other will be 0. For x3, we have, for x3 dot is x4. So only x4 coefficient will be 1. Rest other will be 0. Now for x4 dot, we have x4 dot, this equation 8u minus 5x4 minus 7x2 minus 9x1. So coefficient of x1 is minus 9. Coefficient of x2 is minus 7. x3 coefficient is missing, so it will be 0. x4 coefficient is minus 5, so we will write here minus 5. Coefficient of u is 8, so we will write here 8. So this is our state equation. Now for output y is what? We have taken the output as our first state variable, y is equals to x1, and all the other state variables x2, x3, x4, they are 0. So we will have here x1, x2, x3, x4 plus our input. Input coefficient is also not present, only x1 is present, so we will write here 1 and all other are 0. So this is our output equation. So both these equations, state equation and the output equation, they are going to make the state model of the system. So this is how we can represent the state model of a system which is given in the differential equation form. Now second type is the system which is given to us in the transfer function form. So how we can represent such a system, how we can obtain the state model of a system which is given in the transfer function form. Let's see. Now for the state space representation of a given transfer function, there are 5 methods. First is direct decomposition. First is direct decomposition, second is cascade decomposition, third is canonical or diagonal form, which is also known as parallel decomposition. Fourth is Jordan canonical form, which is also the state model using parallel decomposition. And fifth, we have the state model, which is using the phase variable formulation. So these are the 5 methods by which we can obtain the state space representation for a given transfer function. First method is direct decomposition, second is cascade, third is canonical or diagonal form, also known as parallel decomposition, fourth is Jordan canonical, and fifth is the we are obtaining the state space representation by drawing the signal flow graph. So now we will start with the first method, direct decomposition method. So as this direct decomposition method, it is used for the state space representation of a system which is given in transfer function form. So let's see that how the transfer function is represented. Transfer function of a system is given as the ratio of the Laplace transform of the output and the input, and it is equals to 1 upon. So this is the representation of a transfer function. Now in the direct decomposition method, let's take an example so that you will clearly understand this method. Let's take a transfer function of a system ys upon us equals to 1 upon. We have taken the transfer function of a system. So how we can solve this transfer function by this direct decomposition method? How we can obtain the state model? First step is to represent the transfer function in the form of a block diagram. So here in the transfer function, we have the highest power of s as 3. So n is equals to 3. So when we represent this system in the block diagram form, so there will be 3 integrators, because here the power of s is 3. So there will be 3 indicators in the block diagram. So the differential equation, it is of third order. So there will be 3 integrators and 3 summing points in the block diagram. So let's draw the block diagram for this transfer function. We have the input, 3 summing points. So we will draw the 3 summing points here. And 3 integrators. So we will draw here the integrators. Three blocks showing the integration sign here. This is our input. This is the output 1. Now the output of each integrator will be the state variable. So first this output will be x1, the output of this integrator is x2, and the output of this integrator is x3. So the output of each integrator will be the state variable. Now using the block diagram, and we have the differential equations there. We have the differential equation of the system as s3 plus 6x square plus 11s plus 6. Now we have here minus 6 So these are the three summing points, three integrator, and we have represented the transfer function in the block diagram form. Now the output of this integrator is x3, so its input will be x3 dot. The output of this integrator is x2, so its input will be x2 dot, and the output of this is x1, so its input will be x1 dot. So x2 will be x1 dot, x3 will be x2 dot, and here we have x3 dot here. So this is the block diagram of this transfer function. Now in step number 2, as we have taken that the output of each integrator is the state variable. So using this block diagram, we will write the equations for each of these state variables. Now write the equations. We have in the block diagram x1 dot. So x1 dot will be 0x1 plus x2, because x1 dot is what? X2. So x1 dot will be 0x1 plus we have x2 plus 0x3 plus 0u, because we have x1 dot as x2. Then we have x2 dot equals to x3. So it can be written as 0x1 plus 0x2 plus x3 plus 0u. 0 is written because the coefficients of x1, x2 and u are missing in this x2 dot, and only coefficient of x3 is present. So we have this equation. First, we have this as second, then x3 dot. x3 dot is what? Here x3 dot will be minus 6x3 plus, from here we are getting minus 11 x2, from here we are getting minus 6x1. So here minus 6x1 minus 11x2, and this is minus 6x3. These three, they are getting add up and it is equal to x3 dot. So x3 dot will be minus 6x1 minus 11x2 minus 6x3, and we have u also here. So this will be minus 6x1 plus u. This will be minus 6x1 plus u, this minus 11x2, and this will be minus 6x1 plus u minus 11x2 minus 6x3. Okay. So here we are having plus u also. So these are the three equations for the three state variables, derivative of three state variables x1 dot, x2 dot and x3 dot. Now output equation, that is y will be equals to x1. You can see in the block diagram that we have taken the first variable as y is equals to x1. So y is x1. We can write this equation as x1 plus 0x2 plus 0x3 plus 0u. So we have these four equations. Now using the first, second and third equation, we will write the state equation, and fourth equation is our output equation. As we have three state variables, so x1 dot, x2 dot, x3 dot. So for x1 dot, it is equal to x2. So we will have 0, 1 and 0. x2 dot is equals to x3. So it will be 0, 0, 1. And x3 dot is minus 6x1 minus 11x2 and minus 6x3 plus u. So this is our state equation. Now output equation y is equals to x1. So we will have this as our output equation. So these two equations, state equation and the output equation, they combinedly represent the state model of the system. So in this way, using the direct decomposition method, we can represent a system by a transfer function. Now we will study the second method. The second method is the cascade decomposition. Cascade decomposition, this technique, it is used when the transfer function of the system is given in the form ys by us, it is the transfer function, and it is given in the form of the factors of the differential equation. So we have 1 upon s plus a, s plus b, s plus c, and in this way if the transfer function is represented, that is the differential equation is now factorized. So if transfer function is given in this form, then we will use the cascade decomposition technique. Now let's take an example so that we will understand that how we can get the state model using this technique. Let's take an transfer function. You can see that this transfer function is given in the form 1 upon s plus a, s plus b, s plus c, and so on. So this is, so we can apply the cascade technique here. Now for decomposition, we have the output of 1 upon s1 is given as an input to 1 upon s2, and then the output of this 1 upon s2 is given as an input to 1 upon s plus 3. So we have 3 summing points and 3 integrators also, but here we will have the block diagram as one summing point, one integrator, then another summing point and integrator, then third summing point and third integrator. In the direct decomposition, we have 3 summing points placed close to each other and then 3 integrators placed close to each other. Here we will write one summing point, one integrator, then one summing point, one integrator. So they will be separate for each of these factors. So first is for this s plus 1. So the output of this integrator, it is summed up, and here we have minus 1. This is our u, they are plus. Then we have this integrator and the summing point. Here we will have minus 2. Again they are summed up. For this we have, this is the integrator. Here it is minus 3. Again they are summed up here. And this is our output. Now again the output of each integrator will be a state variable x1, it is x2, this is x3, this is x3 dot, this will be x2 dot, and here we will have x1 dot. So you can see that the output of these in the first integrator is the input to the second integrator, second block, and the output of the second is the input to the third block. So this is how the block diagram, when we are using the cascade decomposition, it is drawn. Now next step is the output of each integrator is the state variable. So let's write the equations for each of the state variable. First we have x1 dot, derivative of first state variable x1. So x1 dot is minus 3x1, and here we have x2. So it is minus 3x1 plus x2. Then for x2 dot, it is minus 2x2 plus x3, and x3 dot is minus x3 plus u. So we can write here minus x3 plus u. We can also write these equations because here we have three state variables x1, x2, x3 and one input u. So the derivative of each state variable, it is a linear combination of the state variables and the input. So here we can write minus 3x1 plus x2. x3 is not present, so we can write its coefficient as 0, and u is also not present, so we can write its coefficient as 0. Here also x1 is not present, so 0x1 minus 2x2 plus x3 plus u is not present, so its coefficient is 0. Here 0x1 plus 0x2 minus x3 plus u. So we have these three equations. Now using these three equations, we will obtain the state equations. The state equations can be written as, we have the three state variables x1 dot, x2 dot, x3 dot. So x1 dot is minus 3x1 plus x2, 0x3 and 0u. x2 dot is 0x1 minus 2x2 plus x3 plus 0u. And x3 dot is 0x1, 0x2 minus x3 and plus u. So this is our state equation. Now second is our output equation. So output is given by y is equals to x1. We have let it as y equals to x1. So our output equation will become because y is only x1, x2 and x3 are not present, so their coefficients will be 0. So this is our output equation. So both these state equation and the output equation, they collectively make the state model of the system. So in this form, if the transfer function is given to us in the factorization form, that is 1 upon s plus a, s plus b, s plus c. So if in this form the transfer function is given, then we can use the cascade technique, and through this method we can obtain the state model of the system. So this was the second method. Now third method is the canonical or the diagonal decomposition, or also it is known as the parallel decomposition. So let us study the third method. So in this canonical or the diagonal form, also known as parallel decomposition, the transfer function, it is split into the factors. We split the transfer function, then we obtain the state model of the system. Like, take an example. Just remember that we split the transfer function into its fractions. So let's take an example. We have a system whose differential equation is given to us. Differential equation is given to us, so we will take the Laplace transform of this equation. Laplace transform will be, here we can also write this as d3y upon dt cube. So this is the differential equation. Now we have to obtain the transfer function, and transfer function is the Laplace transform of output and the input. So we will take the Laplace transform assuming all the initial conditions to be 0. So taking Laplace transform, and assume all initial conditions to be 0. So Laplace transform of this will be, we have s cube ys plus 6s square ys plus 11s ys plus 6 ys equals to us. So Laplace transform, we will write it as s cube ys plus 6s square ys plus 11s ys plus 6 ys equals to us. Taking ys as common, we have s cube plus 6s square plus 11s plus 6 equals to us. Now taking the ratio of ys and us, we will have 1 upon s cube plus 6s square plus 11s plus 6. So this is the transfer function of the system. Okay. Now we have to split this transfer function into partial fractions, because this is our this method is the parallel decomposition. So here we are getting the partial fractions of this 1 upon s cube plus 6s square plus 11s plus 6. So we will split this, we will obtain the fractions of this differential equation, third order, s cube plus 6s square plus 11s plus 6. So it will be s plus 1, s plus 2 and s plus 3. How we can obtain? From here we can have s square as common, then this is s plus 6, then here 11 s plus 6 by 11. If we solve this this equation, this is third order differential equation, then its factors will be s plus 1, s plus 2 and s plus 3 here. So we can write here ys upon us equals to 1 upon s plus 1, s plus 2 and s plus 3. Okay. Then obtain the partial fractions. How we can do this? We have 1 upon s plus 1, s plus 2, s plus 3. So we can write a upon s plus 1, b upon s plus 2, plus c upon s plus 3. Obtain the coefficients a, b, c. We are just doing this using the partial fraction method. So here we will have a, s plus 2, s plus 3, plus b, s plus 1, s plus 3, plus c, s plus 1, s plus 2. This is equals to 1. This denominators, they are cancelled out. So here we will have a, this is s square plus 3s plus 2s is 5s plus 3 to 6, plus b we have s square plus 3s plus s is 4s plus 3. Then c we have s square plus 2s plus s is 3s plus 2 equals to 1. Multiply all these, we have as square plus bs square plus cs square. Then coefficient of s are 5as plus 4bs plus 3cs. Then 6a plus 3b plus 2c equals to 1. So the coefficients or the constant terms will be equal to 1 and all the other will be 0. We have a plus b plus c equals to 0. We have 5a plus 4b plus 3c equals to 0. And from here we have 6a plus 3b plus 2c equals to 1. So we have three unknown variables and three equations. So we can find out the value of A, B, C using these three equations. So A will come out to be 1 by 2, B will be minus 1 and C will be 1 by 2. So we have obtained these values of A, B, C. So our transfer function ys upon us, it will become a upon s plus 1. A is what? 1 by 2 upon s plus 1. Then we have b upon s plus 2. B is minus 1 upon s plus 2. Then we have c upon s plus 3. C is 1 by 2 upon s plus 3. Multiply this us on the right hand side. We will get ys equal to now this ys is equal to, this is x1s plus x2s plus x3s. We have three state variables x1, x2 and x3. Now x1s is equal to 1 by 2 s plus 1 multiplied with us. x2s is this minus 1 upon s plus 2 us, and x3 is 1 by 2 upon s plus 3 us. Okay. Now we have these three equations 1, 2 and 3. So using these three equations, obtain the state equations. Okay, multiply this s plus 1 to the left hand side. We will have x1s multiplied with s plus 1 equals to 1 by 2 us. So s x1s plus x1s equals to half us. Now taking inverse Laplace transform, we get s x1s will be x1 dot plus we have x1 and this is equal to half u. So this x1 dot will be equal to minus x1 plus half u. This is our fourth equation. Similarly, we have x2s equals to this minus 1 upon s plus 2 us, multiply this s plus 2 to this side. So this will become s x2s plus 2x2s equal to us. Again take inverse Laplace transform. We have x2 dot plus 2x2 equal to u. So x2 dot will be minus 2x2 plus u. This is our fifth equation. Now third we have x3s x3s is 1 by 2 us upon s plus 3. Multiply this to this side, s plus 3, x3s equal to 1 by 2 us. Again taking inverse Laplace transform, we will get x3 dot plus 3x3 half u. So it will become x3 dot equals to minus 3x3 plus half u. This is our sixth equation. Now using these fourth, fifth and sixth equation, we will obtain the state equation. So using these three equations, we will obtain the state model now. So we have x1 dot, x2 dot and x3 dot, the derivative of the three state variables. Now for x1 dot, we were having the equation as x1 dot was, this was our equation, x1 dot was minus x1, so coefficient of x1 is minus 1. Coefficient of x2 and x3 is missing, so it will be 0. Coefficient of u is half, so we will write here half. Then x2 dot, we have coefficient of x1 as 0, coefficient of x2 is minus 2 and coefficient of x3 is 0, coefficient of u is 1. Now for x3 dot, we have minus 3x3, coefficient of x1 and x2 are missing, so we will write here 0, and x3 we have minus 3. For u we have half, so we will write here half. So this is our state equation. Okay. Now output equation, we have y equals to, we have taken here x1s plus x2s plus x3s. So if we take the inverse Laplace transform, it will become y equals to x1 plus x2 plus x3. So it is the sum of all the three state variables and its their coefficient are 1, 1, 1. So we will write here 1, 1 and 1. And here we have x1, x2 and x3. And this is our output equation. So both these equations, they will make the state model of the system. So we have obtained the state model of the system when the transfer function, we have split the transfer function into its partial fractions and we have used the method canonical or the diagonal form. Diagonal form it is said because you can see that all the elements are 0 except the diagonal elements. The diagonal elements of the matrix are present. So this is known as the diagonal form also. So whenever you have any question where you have asked that obtain the state model in the diagonal form, where this A matrix, it is in the diagonal form, then use this canonical or the parallel decomposition or the diagonal form of the state space representation. Now next method we have is the Jordan canonical method. So let's study this method. This model is also known as state model using parallel decomposition. Okay. So where we use this method? If the transfer function is having repeated roots in the denominator, then this method, Jordan canonical method, is used for obtaining the state model of a system. Let us again take an example. The transfer function is ys upon us equal to 10 upon. So you can see that in this transfer function we have repeated roots in the denominator. S plus 1 square is there. So we have s plus 1, s plus 1 and s plus 2. So these are the repeated roots in the denominator. So how we will obtain? Now let this ys upon us is equal to we have this division of the, we have decomposed the transfer function into three factors. Now for each of the factors we will obtain a, b and c. So a will be s plus 2, so in this way we will obtain the value of a. Put s equals to minus 2 here, so we will have the value of this as 10. Then b, so here we have s plus 1, so s plus 1 equals to 0. It means s equals to minus 1. So at s equals to minus 1, we will calculate the value of our transfer function, that is 10 upon s plus 2 s plus 1, and we will differentiate with respect to s plus 1. So we will write here d by ds. This is 10 upon s plus 2 at s equals to minus 1, because minus 1 plus 1 it will become 0, so we have 10 upon s plus 2 only, or s plus 1 they are cancelled out. So this is 10 upon s plus 2, so its value will come out to be minus 10. Then we have s plus 1 square. We will write here s plus 1 square, they are cancelled, so we have s equals to minus 1, minus 1 plus 2, 2 minus 1 is 1, so we have c equals to 10. We have obtained the value of a, b, c. So a is 10, b is minus 10 and c is 10. We will substitute the values. This is our transfer function ys upon us. Now let's draw the block diagram for this method. Block diagram will be, here we will have a summing point there. So we have ys upon us equals to 10 upon s plus 2. So we have 10 multiplied with this s plus 2. So for first we have x1, the output of the integrator is x1 and its input is x1 dot, and it will be minus 2, because first we have s equals to minus 2 for this, s equals to minus 1 and s equals to minus 1 for this also. So this is the representation multiplied with the 10. Then for second, multiplied with minus 10, because b is equals to minus 10, and here the third factor is represented and c value is here 10. Now using the block diagram, we will write the state space equations for this system. So first we have x1 dot is equals to minus 2x1 plus u. x2 dot will be u, and this is minus x2. x3 dot is, here we are having x2 and this is minus x3. So in this way state equations will be written using this block diagram. We have x1 dot equals to u minus 2x1 . Now here we have the coefficient of x2 and x3 are missing, so we will write 0x2 plus 0x3 plus u. Here coefficient of x1 and x3 are missing, so we will write 0x1 minus x2 . And the output equation y is, we have 10 multiplied with x1 minus 10 multiplied with x2, and we have x3 multiplied with 10. So we have 10x1 minus 10x2 plus 10x3 is the output y. So we have 4 equations in total. Using these three equations, we will obtain the state equation as x1 dot, x2 dot, coefficients of the state variable x1, x2, x3. Coefficient of x1 is minus 2, 0, 0 and 1. Then x2 dot we have 0, minus 1, x3 is 0 and u is 1. Then coefficient of x1, x2 is 1, x3 is minus 1 and this is 0. So this is the state equation. Now output equation y, we have 10 minus 10, 10, x1, x2, x3. So these two equations, they are the state equation and the output equation, and they form the state model of the system. So in this way we can obtain the state model using the Jordan canonical form. Now next method is the obtaining the state model using the signal flow graph. So let's study the last sixth method. So this method is based on the phase variable formulation by drawing the signal flow graph of the system. Again, take an example to understand this method. Here we are going to draw the signal flow graph of the system. Transfer function is given to us, ys upon us equal to Now let's simplify this transfer function. Here we have the order of the differential equation as 3. So there are 3 state variables. x1, x2 and x3. Let's take here s3 as common and here also s cube as common. So we have ys upon us equal to s cube as common if we take. So it will become 1 upon s plus 3 upon s square plus 3 upon s cube. On here if we take s cube as common, then it will be 1 plus 2 upon s cube and s cube, they are cancelled out. Now we can simplify this transfer function or we can convert it into the form if we take minus sign common here. So this will be minus upon 2 by s minus 5 by s square minus 1 upon s cube. This we have done because we want to convert it in the form of 1 minus GSHS. Okay. So this will be our GSHS. Okay. And this is GS. We have converted it in the form GS upon 1 minus GSHS. Now, if we know that the signal flow graph and the transfer function, they are connected by the Mason's gain formula. So Mason's gain formula, it is given by we have ys upon us, that is the transfer function ys upon xs is equals to p1 del 1 plus p2 del 2, and in denominator we have del. This was our Mason's gain formula. Here this p1 del 1 plus p2 del 2, they are the forward path gains, and del is given by 1 minus So this is how the del is defined, that is the graph determinant is determined. So if we compare this Mason's gain formula and our transfer function which we have obtained here, so this numerator part, it is what? P1 del 1 plus P2 del 2 plus till Pk del k, and this denominator part is del, and this is 1 minus sum of loop gain of all individual loops. So 1 minus, this is the sum of the loop gains of all the individual loops. So this is our first loop, this is second loop, and this is our third loop. Okay, so we have, if we compare, we have 3 forward paths, P1, P2 and P3. P1 will be equals to 1 upon S, P2 will be equal to 3 by S square, and P3 will be equals to 3 by S cube. These are our 3 forward paths because we are comparing this with P1 del 1, P2 del 2 plus P3 del 3. And if we compare the denominator part, so 1 minus this sum of loop gains of all individual loops. So we have 1 minus, these are our 3 individual loops. So 3 individual loops are minus 2 by s, minus 5 by s square, and minus 1 by s cube. Now Further, we don't have any terms, so it means that these loops are, there are no non-touching loops. All the three loops are touching to each other. So using these two information, that is the three forward paths and the three individual loops, we will draw the signal flow graph of the system. So as we have three state variables, we will draw here a straight line. This is our input, this is output. Then we have three state variables, x3, x2 and x1. We have written x1 here because we have taken the output as the first state variable. So when we write here, y will be equals to x1. Now our three forward paths are 1 by s, 3 by s square and 3 by s cube. So we have three powers, the power of s is 3. So we have three integrators will be there. So we will write here 1 by s. Here we will write 1 by s and here we will write 1 by s. Now our first forward path is minus this 1 by s. Okay, so we have starting from here, we will come to this. This will be having 1 plus 1 and this is multiplied with 1 by s and it is equal to the output 1. Then second is 3 by s square. So we have 2 here. Then this is 3. Starting from here, we will have a this is 1. Then 1 by s will be 1. So it will be 3 multiplied with 1, 1 by s, so it will become 3 by s square. And our third is 3 by s cube. So this 3 multiplied with 1 by s, so it will become 3 by s cube and it is equal to y. So these are our three forward paths. Now individual loops, we have minus 2 by s. So we will have minus 2 here. Minus 2 by s. Then we have minus 1 by s cube and minus 5 by s square. 1 by s, we will start from here. We will come to this side. So it is minus 5 by s square. Then we have minus 1 by s cube. So we will start from here and we will go to this side. So this will be minus 1 s cube s. So it will be minus 1 by s cube. So this is the signal flow graph of this system. Now from this signal flow graph we will have the equations. First equation will be y equals to x1. So we can write it as y equals to x1 plus 0 x2 plus 0 x3. Then we have x1 dot, we have to obtain for x1 dot, x2 dot and x3 dot. So x1 will be, from this loop if you see, x1 will be equals to 1 by s multiplied with minus 2y, because here we are having y, so it is minus 2y. It is plus u and also we have x2 coming here. So this 1 by s multiplied with minus 2y plus we have u and plus x2. Similarly x2 is this node. So on x2 we have 1 by s multiplied with this u minus 5y, that is x1, and then x3. So x2 will be 1 by s minus 5y plus 3u plus x3, and x3 will be equal to 1 by s, we have 3u and minus y. So we have three state variables. Now if we multiply this s to the left hand side, then s x1 will become x1 dot, s x2 will become x2 dot, and s x3 will become x3 dot. So our equations will now become x1 dot equals to minus 2, y is what? x1 minus 5, x1 plus 3u plus x3, and x3 dot is 3u minus y is x1. So these are three equations. Now using these three equations, we will obtain the state equation. So now from here we have x1 dot, coefficient of x1 is minus 2, x2 is 1, x3 is 0, and u is 1. So we have minus 2, 1, 0, and 1. For x2 we have x2 dot, we have minus 5 x1, 0, 1, and 1. x3 dot we have 3, sorry, this is minus 1, this is 0, 0, 3, and y is x1, so it will be 1, 0, 0. So these two equations, they combinedly form the state model of the system. This is the state model. First equation is the state equation, and this is our output equation. So in this way, we can obtain the different types of representations of the state model. There are various methods we have studied. First was that the representations, they can be of two types. First is the physical variable form, and second is the phase variable form. In the physical variable form, we studied that how we can obtain the state model of an electrical system and of an mechanical system. Now come to the phase variable form. We know that phase variable form is used when the system is given in the differential equation form or in the transfer function form. We have studied for both the methods. For transfer function, we studied 6 methods: direct decomposition method, then canonical, cascade, then Jordan canonicals, then we studied the signal flow graph, parallel decomposition. We have studied all the methods. So this is how the different types of representations of a state model can be done. So I hope this topic is clear to you. Thank you.